conference was on partial hyperbolicity. So let's start with the definition of partial hyperbolicity. We say diffeomorphism is partially hyperbolic if we can split the tangent bundle into a continuous direct sum of three bundles, so that the vectors in this bundle are exponentially expanded. Whoops, that's bizarre. Are expanded by the dynamics. Okay, let's try that. Expanded by in the unstable bundle are expanded by the dynamics, in the stable bundle are contracted by the dynamics, and there exists this domination condition between the three bundles, the stable, unstable, and the center bundle. So I'll just resort to this cartoon. So EU is an expanded bundle, ES is a contracted bundle by the derivative, and EC is dominated. Okay. So I want to give some examples of partially hyperbolic diffeomorphisms in dimension 3, because they're going to illustrate the work I'm going to talk about, which is joint work with Arthur and Sylvain, and also Alex Eskin and Raphael Potre and Jiwan Zhang. So our first example of a partially hyperbolic system is the automorphism of the three torus given by the following matrix. So this is a trivial example, but let's recall it. So we think of the three-dimensional torus as a circle bundle over the two-dimensional torus. And then the dynamics is simply, it's acts by the Anosov diffeomorphism 2111 on the base and the identity on the circle. And the circles are just permuted according to this Anosov diffeomorphism. And here the center direction is tangent to those vertical circles. Stable direction is tangent to the stable direction of one of these horizontal tori, and the unstable EU is tangent also. A second example. So again, we look at a toral automorphism. But this one is given by a matrix that is irreducible, in fact. And this matrix, I will return to it as it's an example that's discussed in a paper that I will talk about later. So what about this? What can we say about this matrix? Well, it has three eigenvalues. One of them's bigger than one, another one's bigger than one, but less than the first, and the third is less than one. So three real eigenvalues. And so here, the tangent bundle to the three-dimensional torus, it splits as a direct sum in more than one way, more than one interesting way. There's a strong unstable bundle corresponding to the largest exponent, a center corresponding to the middle exponent, and a stable corresponding to the exponent less than one. And the sum of these two bundles gives a two-dimensional unstable bundle. Okay, so it's both partially hyperbolic, it's sort of partially hyperbolic in two ways, in the way with the three-way splitting, and in the way with a two-way splitting as an Anosov diffeomorphism with the trivial center. I want to think about it in both ways, actually. But yeah, so there's the Anosov splitting. And so just a pictorial version of what I just said, the three eigen directions are orthogonal because the matrix is, you can see, symmetric. And so the strong unstable and the center are formed together, they integrate to give an unstable direction. Okay. The third example, so I hope these examples are familiar to everyone, but I'm not assuming much. Okay, third example would be an example of a homogeneous space where we take, let's say SL2R, and we take the quotient by a lattice, so some subgroup, so that this quotient, say, has finite volume. And we consider the map G on this manifold given by right translation by a diagonal and non-trivial diagonal matrix. So this is the same as if you look at H mod gamma. I'm not going to say much more about this example, but if you look at H mod gamma, then M is naturally isomorphic to the unit tangent bundle of H mod gamma, and translation and the map G is isomorphic to the time like 1/2 log alpha, maybe minus 1/2 log alpha. I might have gotten the inverses in the wrong direction. Map of the geodesic flow, which is Anosov. And it has the direction of the flow, the direction, the stable direction, and the unstable direction for the Anosov flow. So this is the in the direction of the generating vector field for the flow. And this map is isometric. Now let me get rid of all this. This map is isometric on the center. I'll move some of this crap. Okay, and for example, if you take SL2Z, where the quotient is not compact, but I'm doing this for a reason, you get a fundamental domain in the upper half plane for the quotient. It is this object here, this infinite object, and the geodesic flow follows geodesic paths. Okay. Anyway, so in this family of examples, the derivative in the center is isometric. So these are all examples on 3 manifolds. And I want to address the following question, which is how do the unstable manifolds for a partially hyperbolic diffeomorphism distribute in the manifold? So I'm going to ask this question topologically. There's also a measure theoretic question that I'm going to say something about a little bit later. But the first kind of basic question is fix a point in the manifold. What is the closure of the strong unstable manifold through X? So remember, the unstable manifold is a manifold that's tangent everywhere to the bundle EU in the 3-way splitting. Okay, and let's just go through these examples. So in the first example, where we had this trivial product of an Anosov diffeomorphism with the identity on a circle, if I take any point and I look at the submanifold, it's forced to stay tangent to a horizontal torus, and its closure is in fact that horizontal torus. So for this example, the closure of any unstable manifold is a submanifold, in fact, but it's not in any way dense in the whole manifold. Now my dog is barking. I'm going to have to ask someone to take care of this dog. Hold on. Okay, the second example, this irreducible matrix, the strong unstable manifold is minimal. So it spans a totally irrational direction in the 3-dimensional torus. And there's a 2-dimensional cartoon of this. And so the closure of every strong unstable manifold is M. And in the third example, I just wanted to give this third example. This is a non-compact example, but here we have a mixed situation. So for most points in the unitangent bundle, if I take the strong unstable manifold through that point, I get this interesting picture. If I let the manifold go to infinity, that object is actually dense in the unitangent bundle. And so for some points, for most points, in fact, WUU or WU closure is all of them. But then, of course, if I take a vector like this, the strong unstable or the unstable manifold is a circle. Okay. That can't happen in the compact setting because the circle would be contracted by the dynamics and you get issues. So, but this can happen in this kind of homogeneous setting. So I wanted to give some kind of aesthetic motivation for the question I'm going to address today, and that's the Ratner's orbit closure theorem. And then there's also Ratner's theorem for measures. What our orbit closure theorem says, it says that if I take any homogeneous space and I take a unipotent flow on that homogeneous space, then the closure of the orbit is going to be a homogeneous space, basically. In particular, it's going to be a nice submanifold. And in these three examples, the WU foliations are actually orbits of unipotent flows on homogeneous spaces. And so the orbit closure theorem actually says that the closure of every leaf is itself a homogeneous space. So in the first example, it's a torus. In the second example, it's everything. In the third example, some leaves are circles, some leaves are the whole quotient, but in any case, they're all very nice. So I posed the question, and I'm going to keep it really vague because I'm mindful that there might be counterexamples if I pose the question too strongly. Well, let me pose it too strongly, and maybe someone can tell me about a counterexample. So is there an orbit closure theorem for transitive partially hyperbolic diffeomorphisms? So suppose I have a transitive partially hyperbolic system and I take a point in the manifold. Is the closure of the strong unstable manifold, say, a manifold? Almost certainly not, right? But under what conditions can we say something about the closures of these strong unstable manifolds? And in particular, I'm interested in the question, under what conditions on F is the foliation for the F minimal? All right. Okay. So that's sort of an aesthetic motivation for the question. There's certainly some serious dynamical motivation. The first appears in a paper of Lorenzo and Raul and Christian. And that is to understand this property of transitivity, or robust transitivity was in fact what they were interested in for partially hyperbolic diffeomorphisms. So robust transitivity implies some form of partial hyperbolicity, something weaker than what I described, because there could be only two bundles. So you might ask, you know, what further implications might there be for robust transitivity? And for example, if you have something partially hyperbolic and it's transitive and the unstable foliation is minimal, then F is actually mixing. So that's not hard to see. So, so the properties of this foliation actually control the dynamics. And probably more interesting, or also interesting, is the study of not the density, but kind of something like equidistribution properties, but it's not quite the same as that, of measures that are absolutely continuous along this unstable foliation. So for example, if I take a Dirac mass and I average it along orbits and I take a weak star limit, I'm going to get a U-Gibbs state. I'm going to get something that is absolutely continuous along the unstable. So these U-Gibbs states play an important role in ergodic theory. They were, I think, introduced by Kessin and Sinai quite a while ago. So for example, if you have a unique U-Gibbs state, then it has to be a physical measure. Okay. Finitely many U-Gibbs states mean you have physical measures. So, so we have examples where we know something pretty strong about what the what the closures are of these unstable manifolds. So let's perturb one of these examples, keeping M just with M compact. So forget about the modular surface example. So what can we say about the behavior of the perturbed foliation? What do I mean perturb? Maybe it's a C1 diffeomorphism that's C0 close to the original, or C1 close, or maybe it's CR. I'm going to keep it pretty vague. There's different things you can say for different examples. So examples 1 and 2 is addressed in this early work of Bonatti-Diaz and Urez. I'm going to at least partially addressed by these examples, by this work. And it's of a fundamentally different flavor than example 3. And example 3, which is Anosov, remember, is what I'm addressing in this talk. Okay. So I'll just say a few words about what did Christian, Lorenzo, and Raul prove. So they posed the problem, as I said, this kind of very interesting general problem. Are the strong stable and strong unstable foliations minimal for an open and dense set of robustly transitive, strongly partially hyperbolic diffeomorphisms? And they focused really on the case where you have a three-way splitting. You're in dimension 3. So your center is one-dimensional, stable and unstable are one-dimensional. And they were interested in the case where you're definitely not an Anosov, where the center is not expanded or contracted. And they used something, I'll just call it a magic horseshoe. Could also call it a blender or a heterodimensional cycle. I realize these things are all a little bit different. But using a magic horseshoe, which, as we've, I think, learned during this conference, Lorenzo played a kind of seminal role in inventing. They were able to prove, so sorry, I said dimension 3, but this is in fact in a dimension. So they proved the following theorem. So you look at robustly transitive diffeomorphisms whose central bundle has dimension 1. This is just one version of what they proved. Is uniquely integrable and is orientable, and orientation is preserved. And then within this class, so these are C1 diffeomorphisms, there's a C1 open and dense set where for any diffeomorphism in this family, you either have a robustly minimal stable foliation or a robustly minimal unstable foliation. So you might say, well, why doesn't this apply to the Anosov example? Well, it does, but it's trivial in that case, because in the Anosov example, we know that the stable direction, remember we had a two-dimensional unstable which split, and the stable direction is one-dimensional, and we already know that the actual stable dimension for an Anosov diffeomorphism is minimal. So there's no, this doesn't tell you anything. But in the cases of the other two examples, you can perturb both of those to be robustly transitive. And then this will tell you that at least one of the foliations has to be open and densely has to be minimal. Okay. So let me say something about the Anosov example. Now, I've motivated.
Amy, I think that Bonatti-Diaz is only for dimension 3. In higher dimensions is Hertz-Ures.
This is literally taken from their paper. So this is assuming, yes, there is, sorry, so there's a later paper by Hertz-Ures, sorry, that I should have mentioned.
Bonatti-Diaz is for dimension 3 and Hertz-Ures is for higher dimensions with central dimension 1.
Okay, so maybe because they assume that the center is uniquely integrable, this is not quite the same result, but this is literally taken from their paper.
Okay.
Maybe the difference is because for having both bundles minimal, you need dimension 3 in that paper. And then Hertz-Ures gives.
Yes, okay, so.
I don't remember.
I'm sorry, I should remember better, but you guys proved that both are robustly minimal, open and densely in a dimension? No,
No,
just one of them.
I think that is what you said, is the integrability of the center.
Right. So these examples happen to have a uniquely integrable center, I think. Or maybe not, actually. They're Plaque expansive, but the center might not be uniquely integrable. So, okay, so this could be, let's take this literally. Unique integrability, as far as I know, of the center for the two examples 1 and 2 for perturbations is unknown. Okay, so this could be kind of a vacuous, theorem, but Federico, Hanna, and Raul eliminated this. Okay, and so sorry, I should have stated that their result as well. I should say that Hanna, and I hope you can make some comments, has had done some very interesting work on dynamical consequences of minimality of the strong unstable. So this is something that, people are still thinking about. Okay. So anyway, I'm actually not going to discuss those examples. I want to discuss the Anosov examples. As I said, I gave as a dynamical motivation I gave some dynamical motivations, which are totally trivial for Anosov diffeomorphisms. They're mixing, we understand for the most part, the ergodic theory of the unstable and stable, but not necessarily the strong unstable and stable. But in terms of consequences, we know pretty much what there is to know dynamically about these examples. But they're still very interesting. And so there's a paper that appeared in Experimental Mathematics a couple of years ago by Gogolyev, Maimon, I'm sorry if I mispronounced, and Kolmogorov. And what they did was study perturbations of the example that I wrote before, which was, I think, oh, great, 2, 1, no, great, now that's not working. 1, 1, 1, 1, 1 or something, or 2, 1. So I'm forgetting, I guess I can read it off right here. So 2, 1, 1, 2, 1, 1 or something. That was the example. So they studied numerically perturbations of this map. And they had studied both conservative and dissipative perturbations. And so here is a picture of, for various values of epsilon, so it's like 0.4, but the same value of epsilon, but for more and more, not iterations, but they took a piece of a strong unstable manifold of this perturbed system. And they took a cross section and they just took longer and longer pieces, and they plotted where this unstable manifold crossed the cross section. And as you can see, for this conservative example, not only do these points of intersection look like they're densely filling up the cross section, but they look like they're actually equidistributed in this cross section. Okay, and even kind of more compelling, I have to erase again. Even more compelling is in this dissipative family here. So in this example, if you perturb it, it will, it doesn't preserve volume, but it preserves a unique SRB measure. SRB measure being one that's absolutely continuous along unstable manifolds, which in this case are 2-dimensional. And they compared in a cross section the conditional. So one could take a piece of unstable manifold and put Lebesgue measure on it and then iterate. We could take a piece of strong unstable, or you could take a piece of unstable. And you once again could look at kind of density in the cross section, roughly. The SRB looks like this.
Sorry, can you repeat how is the picture? So this is a center and a 2-dimensional stable, and you look the distribution.
Here's the 2D. So this is, without describing maybe so much how they produce the picture, This is a picture of the SRB for this perturbed map in cross section. That's what the density looks like.
The cross section is taking, how is taking the, sorry, so the cross section is using the unstable, what is the cross section? Sorry.
Sorry, it's not, yeah, right. It's not a cross section. I think they're using, oh goodness, that's a good point. I guess Andre is not here either. These are conditional, sorry, these are not cross sections. These are cross sections. These are conditionals. Sorry, yes, these are conditionals
Okay.
on WU. Yes, sorry. So here's the conditional on W on the two-dimensional unstable, the SRB, and here is a U-Gibbs state that's produced by taking a piece of strong unstable, a sort of a UU-Gibbs state, taken by taking a piece of strong unstable manifold iterating, and these really look like each other. So it looks like, and in fact, they formulated from this a couple of conjectures. They did it for analytic diffeomorphism. So the first is that if you just take any analytic perturbation of your original linear map, that the strong unstable foliation has a dense leaf. Okay, they were being very cautious. One might even conjecture that it's minimal. And in fact, that turns out to be true, as we'll see. And the second that is that there is a unique U-Gibbs measure. So I guess, yeah, okay. So, so this is kind of the measure theoretic version of and this is based on their experiment. That's sort of the measure theoretic version of the first conjecture.
Sorry, Amy, is it possible to explain where analyticity comes in these conjectures, or this, or you don't?
I mean, if Andre was here, he could explain analyticity. I think it was to be, I was just being cautious because their examples were analytic. I don't
Okay.
I mean, you know, I guess it potentially rules out some kind of local, you know, thing
It's
you
an
might be
open
able to
property.
do.
So assume
What's
that you
the-
can show with at least for one system, you have this property and a stable foliation is transitive. The strong and stable.
Oh, it's
They have some
transitive.
indication that it's an open property.
Is it an open property?
I don't know.
Well, I mean, it is, but I don't think it's a obvious
The linear
fact.
and the perturbation of the linear will not. Well, it's open, so it may be open if you prove it, but it's not because it's inherently open, because the linear will have strong and stable dense, but the perturbation, who knows?
Right. So I think that the analytic was just an abundance of caution that you couldn't produce some local perturbation example. It's a little bit like why you put analytic in, you know, conjectures about coexistence, because they're kind of counterexamples if you don't. Okay. Maybe another way of saying it is they wanted to conjecture something was generic. Right? So you say analytic and that kind of does it. All right. So this map A and its perturbation is an example of what I'm going to call an Anosov diffeomorphism with expanding center. So an Anosov diffeomorphism with an expanding center is just one where the unstable bundle has a dominated decomposition into finer, non-trivial, I said non-trivial, into finer subbundles, okay? And then you have, so I'm going to introduce EUU. Whenever I'm talking about an Anosov diffeomorphism with expanding center, I'm going to use the notation EUU for the unstable in this, the strong unstable. And then this is still an unstable bundle. This center is unstable, but I'm just going to call it EC. And together, these bundles form EU in the Anosov decomposition. All right. So, so for example, the Anosov diffeomorphism that we just discussed. In fact, any Anosov diffeomorphism, any Anosov diffeomorphism in dimension 3 linear one is going to be an example of this, and certainly any perturbation of a linear one is going to be an example. And I don't know if there are examples in dimension 3 of Anosov diffeomorphisms that don't have this property. I don't know. Okay, so I can state our results, and I want to say something about the proofs. So the first theorem is something, so every result I'm going to talk about is going to assume that the dimension of the center is 1. Dimension of EC is 1. There are some results that I think we can show when EC is higher dimensional, but we haven't written them down. So look at CR Anosov diffeomorphisms with expanding 1D center. We need R to be bigger than 1. Then there is a C1 open and CR dense set with minimal strong unstable foliation. Okay, so this is any manifold, any dimension. You just need expanding one-dimensional center. So that's kind of plays a key role. If you let the center be higher dimensional, then you can get kind of a C1 dense set, but I don't know whether it's open. Okay, and you can actually get a C1 generic result, I think. Okay, but that's when the dimension's bigger than 1, and I don't know about R bigger than 1. And the second result, so that first result, I think I said was with, Arthur and Sylvain. The second is, it's like an omnibus, like these omnibus results. So it's with Arthur and Sylvain, Alex Eskin, Raphael Potre, and Jiwan Zhang. So you can imagine this might have been some kind of coming together of minds kind of thing. And maybe the rest of the talk will make clear how that might have gone. So again, we're just going to do a CR with R at least 1, an Anosov diffeom or greater than 1. But now let's do it only in dimension 3. Okay, so we're on the 3-dimensional torus. So for example, the perturbations of the examples that Gogolev et al. Discussed in their paper. Well, the first thing is that the strong unstable is just minimal. Like no matter what, it is a minimal foliation, no conditions. But there are 2 ways for it to be minimal. So one way is what I would call the kind of transverse way. Well, one way is that this is very much like the linear example. And that would be that the strong unstable and the stable, so in the linear example, the strong unstable and the stable being linear foliations are jointly integrable. Okay, so they jointly integrate to get a foliation by 2-dimensional planes. And then there's the other case where they aren't. Okay, but in both cases, if they're jointly integrable, they're minimal. The strong unstable is minimal. The second case I will give a name to, it's what's called the transverse case. And then we have a conclusion about measures as well. So if they are either jointly integrable, which is a highly non-generic situation. Of course, this is not an exclusive or, but either they're jointly integrable or there is a unique UU Gibbs state. By which I mean, if mu is F invariant probability measure and absolutely continuous on WUU, then U is equal to the unique SRB measure. So if it preserves volume, then mu is volume. So that is consistent with the pictures that I showed you from the experiments. All right, so these are the 2 results I want to mention. I am exclusively, though, going to
one
discuss...
question, sorry.
Yeah, sure.
There is this result, I think that is Sylvain, Sambarino, and Potri that they use. I think that they show that when you have partially hyperbolic, that is the center is 1-dimensional. They only have a finite number of attractors. And I don't remember how they do it, but I think that at one point they were trying to use something that the unstable foliation was kind of dense. So the PC where the unstable foliation is dense, and instant attractor only have to be finite. I don't know if it's related to.
No, it is kind of related. So there's a condition that they use, that's this transversality condition. And in the presence, I think C1 open-ended densely, in the presence of this kind of situation where you don't have joint integrability, they prove that you have, in fact, at most finitely many minimal laminations for the strong unstable. And that
because
plays a
now
role.
I'm wondering,
Yeah.
because if you assume extra, so let's assume they are resolved, and then you have the property that you are inside an Anosov class. So it's difficult to have transitive pieces, no? So
Yeah,
it's
I mean,
will be related also as a conclusion of their result.
it's related. We don't use their result,
Uh-huh.
but it uses this very same property, which appears also, I think, in other work of Raphael's. Well.
So in principle, you could have an also in dimension 3.
Mhm.
So not just from the result that is transitive.
Mhm.
However, the strong and stable foliation could produce finite number of classes.
Yeah, for example, yeah.
Okay.
And that's only, I think, a C1 open and dense, or C1 generic. Sorry.
Generic.
C1 generic, maybe. Yeah. All right. So, but this assumes more regularity, but it's kind of a unconditional result, at least the minimality. Are there any questions about the statement of either theorem?
Volume preserving assumption.
No volume preserving assumption. No. In either. Yeah. Other questions? Okay, so I'm going to mention.
Just one. So the CRR bigger than 1 is related to Pessin theory then?
No, it's related to some distortion estimates.
Oh,
the proof. Yeah, I mean, no, I'm sorry. Which result? So in theorem 1, no Pessin. In theorem 2, yes, there's when you do the measure theory part, not the minimality, but the measure theory part definitely uses.
Okay, thank you.
Pessin theory for sure. Okay, so and as I said, yeah.
Let me have now an extra question. Is possible to explain why in the second theorem you need to restrict to the 3 torus, or?
Yes, I will explain completely if I get through the talk.
Okay, thank you.
Yeah, I think there are some general, for the minimality, there's probably some generalizations that you can make, but for the ergodic theory, that's kind of, it's a lack of machinery at this point. There's probably something that you can say.
Are these foliations maybe also uniquely ergodic?
Right, so that's a good question, and I thought about it for a few minutes when I was discussing it with you, Mike, at some point. So the question is whether, which seems to be just a different question completely. So well, there's a few other questions you can ask about the strong unstable foliation. So for example, you could ask, let's say you're in the volume preserving situation, you could ask, if I have any set that is saturated, measurable set that is saturated by the strong unstable foliation, does it have to have measure 1 or 0? Okay, that's I think a kind of ergodicity question. And then there's a unique ergodicity question, which you could phrase as follows. Suppose I take a transversal to the strong unstable foliation and I look at the compact transversal and I look at the return map for that. Is there a unique invariant measure? And as far as I know, these are all different questions. So the uniqueness of the U-Gibbs state is not the same as unique ergodicity of kind of makes sense that it wouldn't be the same because the unique ergodicity of the foliation sort of only cares transversely about the foliation, right? Whereas the U-Gibbs state, you're really looking at measures that have conditional, that have absolutely continuous density. So you sort of know what the density has to be up to a scaling, but you don't know how that density can vary from leaf to leaf. So there's some kind of multiplier that goes on that makes it a different question. So these are all interesting questions. And the question about the ergodicity is the first property that I mentioned, I think is especially interesting for partially hyperbolic systems. I think Mike has asked this question before because it goes to the question of when are partially hyperbolic diffeomorphisms ergodic.
Can I ask a follow-up question, or are you short of time?
Sure. I don't know.
I'll ask it again.
Yes, you can ask a question. Well, who was that? Who wanted to ask a question?
Yeah, it's
Omri,
Lorenzo.
okay.
We don't have to finish exactly. We have the whole afternoon.
Well,
Yeah, I don't think people would appreciate that. I bet
never
people
mind.
are tired.
I'll ask at the end.
Okay. Okay, so the ideas in the proof. So the first is, I guess I'd call it magic horseshoes, but it's, again, some kind of blender type-ish, easier than blenders, but perturbations, it involves isolating an interesting horseshoe in which both acts as a cross section for the strong unstable foliation and in which you can do perturbations. Then there's this property that I mentioned before called S transversality that appears in other work, but it has a very interesting and kind of new role here. And then there's something I call Raphael's trick, which is why we're on T3, or part of the reason you're on T3 in the last example. And then there's quite a bit more that involves Paston theory and kind of not Benoit Quint, but actually kind of Eskin Mirzakhani type techniques that I'm not going to mention at all. So there's the ergodic theory component that I will not mention. Okay, so let's start with the magic horseshoes. Oh, I started at 12:30. I have 10 minutes. Yeah, you definitely can't ask any more questions. All right, and I'm going to go faster.
Actually, you started at about 12:40.
Oh, okay.
Because we have all this extra time. So you have 15 minutes.
Okay, now I'm going to relax and I'm just going to go for another hour. All right. So what do I mean by a magic horseshoe? So here we're in the situation where the center, just the dimension of EC is 1. So this is in the setting of theorem 1. Great. This isn't working. Can't write on this. Oh. So this is in the setting of theorem 1. So it's Anosov with expanding center, and the center is one-dimensional. So here we construct for any Anosov in any dimension with this three-dimensional or one-dimensional center, a horseshoe that has the following properties. So here's some kind of boxes in the generation of the horseshoe. There's another like horseshoe that's kind of off stage that's also playing a role, but I just want to simplify this. So this horseshoe is going to have two properties. So first, it's going to be a cross section for any invariant WUU lamination. Okay, so the closure of any strong unstable manifold has to hit this cross section. Okay, and so something like this. So this is actually not, this part is not so hard to construct. The second property is that it is, and I want this to be a stable property. So stably a cross section. So if I do a perturbation, it will remain this way. And that it is robustly perturbable. And I mean this in the following sense. Suppose I have an open set. So here's what I'm trying to prove. I'm trying to prove that right now, I just want to prove that the CR generic such Anosov diffeomorphism has minimal strong unstable. So that's what I want to prove. So by bare category theorem tricks, it suffices to show that if I have any open set U by an arbitrarily small perturbation, I can arrange that every leaf of WUU meets U robustly. Okay. And then you do countable basis, blah, blah, blah. All right. So here's an open set U. And I'm going to consider, so it suffices to show that, in fact, it suffices to show that any, so there's a little more you want to say, but it suffices to show that if I have any WU laminated set that is F invariant, then it meets U. Okay. So I'm going to assume that I have some collection of strong unstable manifolds that's actually invariant. So it suffices to show that some iterate of U meets, some iterative U meets this horseshoe. Not just meets this horseshoe, but meets every strong unstable manifold. So here's the kind of box that generates the horseshoe. The fact that F is transitive because it's an Anosov implies that there's some iterate of U that meets this box. And then I could keep iterating into much smaller scales. And it's going to meet a lot of these kind of the stable saturate, if you like, of many of these little boxes, okay, of the horseshoe itself, or just these boxes. And it's going to occupy a definite proportion of these boxes. Okay, so here I'm using some distortion estimates. I'm using the one dimensionality of the center. And I can keep on iterating and kind of looking in smaller and smaller scales, and U is going to, well, it's going to occupy kind of less and less proportion, but like in a way that's decaying exponentially in a way that I can control very slowly. And then on the other hand, I have my WUU lamination, and I know, well, if I want the leaves, every leaf to meet U, I actually only have to make finitely many of these leaves meet U, because U has some definite thickness in this box. And so if I do this on the right scales, I use a probabilistic argument, which is similar to an argument that appeared in an earlier work with Sylvain and Arthur. By just translating boxes at small enough scales, I can arrange, just by translations in the center direction, I can arrange that finitely many leaves are going to meet F to the minus n, some iterative U. Okay. And that I can do this and still maintain the properties I want for my magic horseshoe under perturbations. So that's roughly how you prove CR genericity. You have to construct these horseshoes. The fact that you can perturb these independently, the reason you can do that is there's some, like, as I said, there's another horseshoe hidden in the wings that's kind of keeping things under control. Okay, but that gives CR genericity. So now what's S transversality? So remember I said C1 open and CR dense. So far I've got CR dense or CR generic. S transversality is something that'll give me openness. Okay, so what is S transversality? So we say that the strong unstable, remember one-dimensional center, has this property, this transversality property. If for every point, if I look at the leaf of WUU through that point, I can find 2 points, Y and Z, so that the following picture occurs. So this is the projection along stable manifolds. It's some continuous. Well, in fact, in dimension 3, it's C1, but in general, it's just a continuous or Holder continuous map. So the picture is the following. So I take X and I can find 2 points, Y and Z, that are both on this strong unstable of X. They're connected by a local stable manifold. And if I project, you can sort of see in this picture, this is my ES direction. If I project like this piece of curve onto the two-dimensional unstable manifold of Z, I'm going to get something that's topologically transverse. Okay. So in fact, you can kind of see it with your eyes that it has to be topologically transverse, right? I mean, it looks transverse. If I do a little projection, it's not really going to change that. Okay, so this is S transversality. Okay, so any point, and in fact, you can show, I mean, if I have any point, if I have this property, then I only have to go out a finite distance before I can find these 2 points, a bounded distance. Okay, so in fact, this S transversality condition is an open property. It's C1 open. Okay. It's not hard to see that minimality of WU implies S transversality if I relieve this dense. Sorry, that's not quite correct.
Could be joint integrable, no? And also still
No, this is not correct. What I said is wrong. Because in the case where EU plus ES is jointly integrable, or sorry, EUU plus, this is not, does not, it's like the opposite. Okay, so I made a little mistake. What I should have said is that generically, if I have minimality, then I have S transversality. So minimality plus a small perturbation gives S transversality. Now S transversality, on the other hand, implies minimality, and I'm going to describe that in the next few slides. So this implies that minimality, it's not quite C1 open, but minimality densely. So densely, WU minimality is C1 open. Or if you like, minimality plus S transversality is C1 open. Okay. So why does S transversality imply minimality? Okay, so here's the second argument I wanted to give. Okay, so I'm going to draw a picture starting at X, but the final proof, I'm actually going to have to take backward iterates. I'm going to start at some point, and then I'm going to look at F to the minus N of X. So I hope you'll forgive me. This should just give a feel of the argument. So suppose I have some point X, some arbitrary leaf, X is arbitrary. Then within a bounded distance of X, I can find such a Z with this transversality property. So Z is connected to some Y, but I'm actually not going to draw this Y. What I am going to draw is the center manifold through Z. There doesn't actually have to be a center manifold, but in this example, whoops, there is. Okay, so did I lose everything? Nope, you guys don't see it. Okay, I think I have to. I have to stop sharing. I have to stop sharing. Why is it doing this? There we go. I'm going to log back into Zoom. Share screen. Do you see me? Yeah, okay, start broadcast. I cannot wait to be back in person. All I can say. Okay. Here we go again. Here's X. There's Z. There's the center manifold through Z. Basically, intermediate value theorem kind of argument shows that I can find 2 points, one on the center manifold of Z and one on WUU of X. That's what this is, blue thing, connected by a stable manifold. Okay. And I can make, things on appropriate scale. Now I just want to look at this little piece over here of strong unstable manifold. let's just focus, forget about X now, and let's look at this picture. What if we iterate this picture forward? What's going to happen? Well, the center manifold will expand, right? So these 2 points are going to move far apart or move apart. This thing is going to get longer, and this is going to get shorter. So if I started with those things really close together, then they would stay really close together. But as I iterate forward, in any case, so I have to kind of imagine going backwards and making things very close to each other, which I can do. In the limit, what I'm going to get is, so these are not on the same center manifold, but if I take a limit, I'm going to get two strong unstable manifolds that are on the same center. So these are both local strong unstable manifolds. And because the dimension of the center is 1, these are going to be evenly spaced, right? Even out to like a pretty long distance, as long as I fix in advance the distance I want. So that's a center bunching kind of condition. It's a little bit stronger than that, actually. And so now I'm going to repeat my argument. Okay, so now I have these two things. And if you want, we could pretend these are extremely close to each other, but at an evenly spaced distance. Now I go out some distance and I find a point Z again. And I draw a center manifold and I make a connection like this. And then I localize my picture. Now I have this picture and I iterate and I now get 3 evenly. If I pick my things correctly, I will get 3 lines that are evenly spaced, meaning this distance is actually, this distance are comparable. And I can continue this argument and get more and more evenly spaced lines. I actually have the freedom to make these as close as I want. I can make this distance as small as I want by going backwards appropriately. And then I take another limit. And what I'm going to get is, this is a WU disk. And what this is in the closure. So remember, I think I forgot to say this, but I had lambda some WUU invariant laminated set. And these line segments, these segments here, or disks, all come from WUU. They all come from this set by the fact that the set's invariant and by this simple argument that I just showed you. And so I can continue to iterate this and I get that my set lambda actually contains a WU low disk. All right. So any F invariant WU lamination can contain a disk if I have the transversality property. And then the minimality of the unstable foliation is going to give you that any F invariant lamination actually has to be everything. Okay. So WU is minimal. So that's why S transversality implies minimality. Okay. And so this together, these two arguments give you the first theorem. So the density comes from the magic horseshoes and the openness. So magic horseshoes not only give minimality, but they give S transversality. And then you get the openness. Okay, I'll just say a couple things about the second theorem, just a few more slides. So I want to discuss why this is always minimal. Okay, and so this is Raphael's trick. Okay, so what do we know in dimension 3? We know that if you have S transversality implies minimality, right? So S transversality implies minimality. Okay, it's not working. S transversality of WUU implies minimality. I see why it doesn't work.
We cannot read when you write.
Okay. S transversality implies minimality. Really? This is worse than what Federico? This is worse than Federico, you're telling me.
No, only Sensei started, Amie. She didn't complain during the talk of Federico. Then,
No, she didn't.
Then.
All right.
She,
No,
she
she
simply
did actually
complained.
complain. All right. Okay. So all I need to show is that if S transversality does not hold, I want to show that EU and ES are minimal. And in fact, I'm going to show more. I'm going to show that I'm going to show that WUU is minimal, even without S transversality. Okay. So I lift to the universal cover. So over here, I have the lift of F, and I have its strong unstable foliation. Then I have the lift. This is the conjugacy, the lift of a conjugacy to a linear map over here in R3. So over here, I have A acting. And it suffices to show that the image of this linear foliation, this foliation is actually linear. Because if I can show that it's linear, then I have a linear A invariant foliation over here. But then that has to be, basically it has to be the strong ones you can show with a little more work, that it has to be actually WUU. WUU of A. And once I've shown that, that implies the minimality. Okay. It also implies this joint integrability. So suppose not. Okay. So here's Raphael's trick.
Say it again, please. So you take the, sorry. Okay.
No. I'll say it again. Sure.
Yeah. You take the lift, and then you take this, say the the conjugacy with the linear part, and you send the foliation of one into the other.
I'm going to show that. And in order to do that, it suffices to show that this is linear.
It's enough to show,
that it's linear. So because the image foliation, so a priori, if I go over here, I just get some invariant Holder crappy foliation. But it does subfoliate WU because H takes WU to WU and WS to WS. But if I can show that it's a linear subfoliation, I claim that it actually implies there's only two things it could be. It could be either WUU of A or it could be WC of A, and it can't be WC of A. So it's WUU of A. So if I can show this for these lifted foliations, that tells you that the conjugacy from structural stability takes the strong unstable foliation for F to the strong unstable foliation for A. This is minimal. Okay. And so
you say that showing that it's linear is the let's say the tool that you are using to send the strong foliation and send one into the other.
Yes. Okay. So I'm going to show that it's linear. And now I say, suppose not. Okay, so this is what I want to show. I say, suppose not. Okay, so I'm assuming that S transversality does not hold. I'm assuming that the image of this foliation is not linear, and I'm going to get a contradiction. So I say, well, if it's not linear, then there's some point where the image is not linear. So maybe it looks like this. Could look much worse. But the point is, if this is not a line, then I can find points in the following configuration where I connect these two with a line, and the image of the leaf is strictly above there. All right. So this is inside of a WU leaf, right? We're inside of it. This is a plane. And it's the image of some point. So now let's look at this picture in dimension 3. So we're in R3. So here's this plane. Here's this image leaf. And now what I want to do, I'm in R3, so I want to look at all of its translates by the fundamental group of the torus. Okay. Now, so these downstairs are all projecting down to the same strong unstable leaf. Yeah. Get rid of all these arrows I keep drawing. Okay. Next, consider the stable foliation. Okay, and consider the projection along the lifted stable foliation onto this unstable manifold. Okay, so the strong stable foliation is totally irrational, right? It's minimal itself. And so the projection of anything, any lift of anything is going to be dense over here. And so in particular, I can find something, one of these things here that projects as close as I want to this original picture. So in particular, back in this unstable manifold, I can find a projection like this. And so this is the projection of some lift, but it's lying on the same strong unstable manifold. Okay. And the projection along strong stables for the linear is just the conjugate of the projection along the strong stables for the nonlinear. So what we have here, if you believe this picture, holds in general, is a point of topologically transverse intersection between the projection of this lifted thing and of this translated thing and itself. What does this correspond to? This corresponds to two pieces of the same strong unstable manifold, a piece of stable manifold. So the linear, it's true for the linear, but it's also pulls back to the nonlinear picture, where the projection of one along the other is topologically transverse. And you can make those as close as you want by just iteration. And so this implies S transversality. So it's a contradiction. Okay, and so therefore, the projected foliation is linear, and therefore it's minimal as well. Okay, so just a couple questions because I know I've gone over. So what we wanted to prove was that not only is it always WU always minimal, which is true, but that you always have a unique Gibbs measure. That would make a kind of nice, clean result. No idea how to do it.
Can we go back? No, really, it's only to understand this last part to the previous slide.
Yeah.
So the S transverse, you say that the contradiction is with the fact that the linear system do not have the S transversality.
Yeah, so no, the nonlinear. So the nonlinear system, right? Nonlinear, not transverse, not S transverse, implies that H of
okay.
is linear. That's what I've proved. Because I assumed if it's not, then I get a contradiction. Yeah.
Yeah, but you are proving that it's not transverse under the image of your conjugacy. So okay, but the non-transversality on the, so the transversality is something that's going to be preserved by the conjugacy.
In this particular case, because you have to say what have I drawn here? So this has no meaning. This foliation has no meaning for the linear case. It doesn't mean anything.
So this is the image of the unstable of F.
Yes.
Unstable.
Mm-hmm.
And you prove that if you don't, so it's not linear, then the images are going to be not transverse.
Then, right, then over here, they're not transverse.
Good. And so, but this implies that well, now you produce transversality. And so, but this is going to be produced, it will be preserved by conjugacies.
Yes, because this foliation came from the actual foliation.
Okay, so,
so
the transversality and non-transversality is a property that is preserved by conjugacies.
No, because this foliation this foliation here is not, there's an actual linear foliation for A. I haven't even mentioned this.
No, I
foliation.
know, but they're saying that you have non-transversality, the image, whatever it is, also have non-transversality respect to the stable foliation.
Right, because the stable foliation is preserved.
Okay,
the
good.
lift.
So this is the main point. Perfect. Thank you.
Yeah. So the conjugacy from structural stability always preserves, or the Franks-Manning conjugacy, whatever, it always preserves the stable. Yeah. Okay, so the first question, I don't know. Second question is an interesting question posed by Raphael in a paper in 2014, I guess based on his thesis. So he asks, is there an isotopy class of diffeomorphisms for which partial hyperbolicity implies chain recurrence? One might ask the harder question, because if you look for stable ergodicity, the answer is yes, the analogous question. In fact, something kind of stronger holds. But so it's a very interesting question, and he proved that on the three-dimensional torus, if you're partially hyperbolic and you're isotopic to an Anosov, you have at most one attracting chain recurrent class and most one repelling. And so my understanding is that using this kind of transversality type of argument I showed with a disk, you can actually, Raphael thinks that, or is able to actually answer this question in the affirmative. So in the isotopy class of any Anosov and T3, partial hyperbolicity does imply chain recurrence. So this is kind of work in progress. And I think I'll end there. Happy birthday, Lorenzo. Oh, one more thing I want to do, sorry. I'm going to put in the chat window a link. There's just going to be a very short little problem session / conference in honor of the 80th birthday of Charles Pugh that happened a year ago. Everyone's welcome. It's just a half-day thing. It's a problem session, short talks. Should be fun. Anyway, happy birthday, Lorenzo. And here's to many more years.
I'd like to thank Amie for this beautiful talk. And I guess my duties as chair are over and we go to the open session with Zay, right?